Good morning. In this section, we will discuss how to interpret nested quantifiers. For example, we will discuss the meaning of there exists y for all x, q of xy, and similar statements. As in our previous lectures, we conclude with several exercises from our text. Example 1. Express for all x there exists y, x plus y equals 0, without the existential quantifier. Solution. For all x there exists y, x plus y equals 0 is the same as for all x, q of x, where q of x is there exists y, p of xy, and p of xy is x plus y is equal to 0. Example 2. Translate for all x, for all y, x greater than 0 and y less than 0 implies xy less than 0 into English. Solution. This statement says that for every real number x and for every real number y, if x is greater than 0 and y is less than 0, then the product xy is less than 0. That is, this statement says for real numbers x and y, if x is positive and y is negative, then xy is negative. This can be stated more succinctly as the product of a positive real number and a negative real number is always a negative real number. The order of quantifiers. Example 3. Let p of x be the statement x plus y is equal to y plus x. What are the truth values of the quantifications for all x, for all y, p of xy, and for all y, for all x, p of xy, where the domain for all variables consists of all real numbers? The quantification for all x, for all y, p of xy denotes the proposition for all real numbers x, for all real numbers y, x plus y is equal to y plus x. Because p of xy is true for all real numbers, x and y, it is the commutative law of addition, which is an axiom for the real numbers. The proposition for all x, for all y, p of xy is true. Note that the statement for all y, for all x says for all real numbers y, for all real numbers x, x plus y is equal to y plus x. This has the same meaning as the statement for all real numbers x, for all real numbers y, x plus y is equal to y plus x. That is, for all x, for all y, p of xy, and for all y, for all x, p of xy have the same meaning. Both are true. This illustrates the principle that the order of nested universal quantifiers in a statement without other quantifiers can be changed without changing the meaning of the quantified statement. Example 4. Let q of x denote the statement x plus y equals 0. What are the truth values of the quantifications? There exists y for all x, q of xy, where the domain for all variables consists of real numbers. The quantification, there exists y for all x, q of xy, denotes the proposition there exists a real number y such that for every real number x, q of xy, no matter what value of y is chosen, there is only one value for x for which x plus y equals 0. Because there is no real number y such that x plus y is equal for all real numbers x, the statement there exists y for all x, q of xy is false. The quantification for all x there exists y, q of xy denotes the proposition for every real number x there is a real number y such that q of xy. Given a real number x, there is a real number such that x plus y equals 0, namely y equal minus x. Hence the statement for all x there exists y, q of xy is true. Example 4 illustrates that the order in which quantifiers appear makes a difference. The statements there exists y for all x, q of xy, and for all x there exists y, q of xy are not logically equivalent. The statement there exists y for all x, p of xy is true if and only if there is a y that makes p of xy true for every x. So for this statement to be true, there must be a particular value of y for which p of xy is true regardless of the choice of x. On the other hand, for all x there exists y is true if and only if for every value of x there is a value of y for which p of xy y is true. So for this statement to be true, no matter which x you choose, there must be a value of y, possibly depending upon the x you choose, for which p of xy is true. In other words, the second case can depend upon x, whereas in the first case, y is a constant independent of x. From these observations, it follows there exists y for all x, p of xy is true. Then for all x, there exists y must also be true. However, if for all x there exists y, p of xy is true, it is not necessarily the case that there exists y for all x, p of xy to be true. Okay, in table 1, we have some nested quantifiers in column 1, and we have conditions when they are true and when they are false. So the first statement in the first row is for all x, for all y, p of xy. P of xy is true for every pair xy. When is it false? There is a pair xy for which p of xy is false. For all x, for all y, for all y, for all x, p of xy when is it true? The same as in the previous case. P of xy is true for every pair xy. When is it false? There's a pair xy for which p of xy is false. For all x, there exists y, p of xy. When is it true? For every x, there is a y for which p of xy is true. When is it false? There is an x such that p of xy is false for every y. There exists x for all y, p of xy. When is it true? There is an x for which p of xy is true for every y. When is it false? For every x, there is a y for which p of xy is false. There exists x, there exists y, p of xy, or there exists y, there exists x, p of xy. There is a pair xy for which p of xy is true. When is it false? P of xy is false for every pair x and y. Example 5. Let q of x, y, and z be the statement x plus y is equal to z. What are the truth values of the statements for all x, for all y, there exists z, q of x, y, z, and there exists z for all x, for all y, q of x, y, z, where the domain of variables consists of all real numbers. Solution. Suppose that x and y are assigned values. Then there exists real number z such that x plus y is equal to z. Consequently, the quantification for all x, for all y, there exists z, q of x, y, z, which is the statement. For all real numbers x and for all real numbers y, there is a real number z such that x plus y equals z, is true. The order of quantification is important because the quantification there exists z for all x, for all y, q of x, y, z, which is the statement. There is a real number z that for all real numbers x and for all real numbers y is true, such that x plus y is z is false because there is no value of z that satisfies the equation x plus y equals z for all values of x and y. Translating mathematical statements into statements involving nested quantifiers. Example 6. Translate the statement, the sum of two positive integers is always positive, into a logical expression. To translate this statement into a logical expression, we first rewrite it so that the implied quantifiers and the domain are shown. For every two integers, if these integers are both positive, then the sum of these integers is positive. Next, we introduce the variables x and y to obtain for all positive integers x and y, x plus y is positive. We can express the foregoing as for all x, for all y, x greater than 0 and y greater than 0 implies that x plus y is greater than 0, where the domain for both variables consists of all integers. Note that we could also translate this using positive integers as the domain. Then the statement, the sum of two positive integers is always positive, becomes for every two positive integers, the sum of these integers is positive. we can express the statement as for all y, x plus y is greater than 0. Translating from nested quantifiers into English. Translate the statement, for all x, c of x, or there exists y, c of y, and f of xy into English, where c of x is x has a computer, f of xy is x and y are friends, and the domain for both x and y consists of all students in your school. Solution. The statement says that for every student x in your school, x has a computer, or there's a student y such that y has a computer and x and y are friends. In other words, every student in your school has a computer or has a friend who has a computer. Translating English sentences into logical expressions. Express the statement, if a person is female and is a parent, then this person is someone's mother, as a logical expression involving predicates, quantifiers with a domain consisting of all people and logical connectives. Solution. Step 1, f of x, x is female. 2, p of x, x is a parent. 3, m of x, y, x is the mother of y. For all x, f of x and p of x implies there exists y, m of x, y. Or for all x, there exists y, f of x and p of x implies m of x, y. Example 13. Use quantifiers to express the statement, there is a woman who has taken a flight on every airline in the world. Solution, let P of W, F be W has taken F, and Q of FA is F is a flight on A. We express the statement as there exists W for all A, there exists F. P of WF and Q of FA, where the domain of discourse for WF and A consists of all women in the world, all airplane flights, and all airlines respectively. Negating nested quantifiers. The complement of there exists xp of x is for all x the complement of p of x. For every x, p of x is false, that's when it's true. And when is it false? There is an x for which p of x is true. And the complement of for all x, p of x is the equivalent statement, there exists x, the complement of p of x. When is the negation true? There is an x for which p of x is false. When is it false? P of x is true for every x. Express the negation of the statement, there exists x, for all x there exists y, xy equal 1, so that no negation precedes quantifier. Solution, by successively applying De Morgan's laws for quantifiers in table 2 section 1.3, we can move the negation, the complement of for all x there exists x, xy equal 1 inside the quantifiers. We find that the complement of for all x there exists y, xy equal 1 is equivalent to there exists x, the complement of there exists y, xy equal 1, which is equivalent to there exists x for all y, the complement of xy equal 1. Because the complement of xy equal 1 can be expressed more simply as xy not equal to 1, we conclude that our negated statement can be expressed as there exists x for all y, xy not equal to 1. Example 15. And I think we'll save that for next time.